Hello and welcome to the UFS webinar. This webinar is hosted by the National Weather Service Office of Science and Technology Integration. The goal of this webinar series is to enhance communications and share advancements in all aspects of the UFS in both research and operational setting. I am Stacy McKell and I'm here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. Also, if you have any recommendations for speakers that you would like to present at this webinar, please send your recommendations to ufs.modeling@noaa.gov, and we'll take your suggestions into consideration. Today's webinar will be in listen-only mode due to the high number of attendees. If you have any questions now or during the event, please submit them on the Google document that will be provided in the chat box. The presentations last about 45 minutes, followed by questions and answers, excuse me, for 15 minutes. Type your questions on the Google document during the presentations. Today's presentation is broad community development of the unified forecast system using the WaveWatch 3 wind model as an example. And today's presentation is by Hendrik Tolman, and my colleague Caroline Delgado will be presenting. Will be introducing him. Caroline, I will turn it over to you.
Thank you very much, Stacy. I'm sure everybody's very familiar with Dr. Hendrik Tolman, who is the Senior Advisor for the Advanced Modeling Systems of the Office of Science and Technology Integration of the National Weather Service. Before joining the OSTI, he was at the Environmental Modeling Center of the National Weather Service for more than 20 years as a wave modeler, and the Marine Modeling Branch Chief and Director. Currently, Dr. Tolman holds a doctorate and engineering degree from the Civil Engineering Department of Delft University of Technology in the Netherlands. He is a naturalized U.S. citizen of Dutch origin. And with that being said, please enjoy your presentation by Dr. Tolman.
Thank you both. See if I can get this working. Yep, there it is. Sound check, you can hear me good, I hope. Stacy, can you hear me?
I can hear you.
Okay, good. Can you see my screen?
I can see it.
Title slide. Okay, then let's get started. So in case of truth in advertising, this is a presentation that I developed before about 2 weeks ago, a one-day workshop at University of Cambridge in England. And the idea was to talk about physics, wavy physics, but also about how we do that with the broader community, how we use AI and machine learning with that, and how we starting to involve the private sector in that. So this is quite a different type of presentation than we normally do. And in truth of advertising, I literally use exactly the same slides that I used for the other presentation, and therefore you will see on the bottom of the slides that this is actually at Cambridge. And so what I was talking about there, it's going to be a little bit faster this time around, about what the UFS is, talk a little bit about the role of WaveWatch in the UFS, and then talking about a bunch of things that are associated with multidisciplinary work, with community building, with AI, machine learning, and with the private sector. And so that is all focused on WaveWatch, and then looking forward particularly on the type of things that we think we can be doing with, particularly with AI and machine learning for these kind of models in general. So starting with the unified forecast system, so most of you should be knowing pretty much everything I'm going to say here, and I'm going to go through this a little faster so I can spend a little bit more time on the parts on AI and machine learning. We all know the website. We all know the original picture of the quilt on the left side in the more unified version of the operational system that we want. On the right side, the importance of starting from requirements and then figuring out what kind of products we need, and then have a unified approach to create these products, instead of the past where we implemented solutions for individual problems rather than starting from a holistic beginning point. We all have seen this slide quite a bit about why we do the UFS. The purpose is doing community developed research and operations with the same system. The fact that we do evidence-based decision making, which is something that is good to keep harping on, but it's something that we in reality have done for a long time. The fact that unlike, for instance, the warfare community, we are looking at applications rather than just at the code itself, because applications are actionable and measurable, whereas the code itself tends to be not that way. Very important is that we're talking about a unified system, not a unitary system. This is a business model where we want to have as much focus as possible on a small amount of software and a small amount of applications, but at the same time have the diversity we need to be able to fulfill all our requirements for our users in terms of the products that we create and how good they are. And it is really neat to, from my perspective, to see over the last few years how we really have changed the culture of how we're doing business, in the sense that we are, but most of us are really working on this unified system instead of on standalone stovepipes in the old production suite. One of the things that is always important to show is that this is not just a NOAA thing, and so this is Community 101. If you see, this slide was created by Cecilia De Luca for the 2020 AMS meeting. You can see the amount of component models we have in the white boxes. You can see the glue in terms of the ESMF, NUOPSI, and NEMS coupling infrastructure. You can see the data assimilation driver over top of that. But more importantly, along the bottom, there are 7 different agencies that are working with us, or 6 other agencies that are working with us on this system. There are already university partners and industry partners, and this is almost 3 years ago. So by now, actually, that group is still expanding significantly. The thing that also is pretty clear, of course, for this group, but was very interesting to show when I go on the road, so to speak, is the fact that we are no longer talking about a fun idea of being able to do something like a UFS, but that we actually have something to show for that. And so in red, you see the implementations that we've had in operations with the GFS v17 soon to be added to that, hopefully. In blue, you see all the different releases we had, including the very recent short-range weather app. And we have to realize, of course, that MET, CCPP, JEDI, and all these other things are all community components that are part of this UFS. So far, most of you will be very familiar with what I've shown. Now I'm going to switch over to my own experience with the WaveWatch 3 WaveWatch model. First of all, if you look at what is now the UFS weather model, that already has the wave model in there as a component. And it is really neat to see that we are doing a much more holistic approach to the entire environment, and not just looking at different components individually. And interestingly enough, particularly when I'm in Europe, then I usually get some pushback about the fact that we haven't coupled waves to the atmosphere for quite a long time, whereas they've been doing that at the European Center for like 15 years. But if you do evidence-based decision making, then there was not that much evidence to actually do that in operations. And specifically, if you just look at the science reasons for that, but from an engineering perspective and from an efficiency perspective, now we go look at the UFS as a system that should run much more efficiently. Then at least one-way coupling becomes a really big deal for being able to efficiently run the UFS. And also, although the physics may not necessarily be having very strong proofs of having to need to do the coupling, the more higher resolution forcing that we get in the wave model by coupling at a more close to a time step level is actually already giving much better wave results, as we've shown over the last 10 years that we would expect there. It's not only the wave model here in the UFS weather model coupled system. There are applications that are much more wave focused too, that are effectively part of the UFS, particularly wave and surge coupling. And thanks to the Coastal Act funding that we had over the last 6 or 7 or 8 years, we are now able to run a storm surge model and a wave model on triangular grids with very close coupling in terms of the effect of the waves on the coastal storm surge. And I could go a little deeper into the graphics here, but the idea here that you have a large domain over the northern Atlantic, and
Hello?
yet, yeah.
And sorry, we're not seeing your slides advance.
Okay, I have no idea what I need to do about that because I'm on slide 10.
Wow. Yeah, I should have caught that earlier, but now I thought you were, giving your introduction, but no, we're not seeing your slides advance. They were advancing before when we was troubleshooting, but I don't see them now.
Okay, what do you see right now?
I see your beginning page, the title page.
Yeah, because I'm not even sharing that right now. I have no idea where you see that because I switched that off right now.
That is exactly what I'm seeing. And you are the presenter. Excuse me.
Okay, so can I give you, okay, you still see the same thing now?
Still see the same. No, now I see just you. I don't see anything there but you.
Okay, because now I don't see myself on my screen anywhere.
Oh, we see you.
Okay, so let me see if I can find,
I have it. Your slides.
yeah, can you take back presenting because I can't even see it. At the moment, I cannot even see where. Thank you.
Go.
Yeah, so on this slide, we have just the other example from the fact that it's not just the global weather model that we were looking at, but this is the example of having the EDSRC storm surge model and the WaveWatch model both running on a triangular unstructured grid, two-way coupled. And in many cases, it's really important to do this in a coupled way because many times the storm surge is actually driven by the waves and not by the local wind. The other thing which is kind of cool to see as a technology here that is built into the UFS infrastructure right now, thanks to this specific application, is the fact that we're looking at a very large area here, but the coastal resolution for this model is as good as 250 meters, thanks to the unstructured grids. And if I had some more time, I would show you some blow-ups and things like that to show that you get enormous detail, particularly in places like Puerto Rico, where this Hurricane Maria went right over top of. So next slide, please. So the things that we were talking about in Cambridge were about starting out about the multidisciplinary, how important it is to be multidisciplinary and how important it is in that context to have a community. So next slide, please. So this is the governing equation for the wave model. One click, please. So in the wave model, we don't describe individual waves, but we describe the energy distribution of wave components over wave number and direction in the so-called wave action variance spectrum. And to begin at the beginning with doing this multidisciplinary, we actually stole this from work from the Bell Labs in the 1940s in terms of radar development that was done for World War II. So the basis of just the way we describe the wave field is already taken from another field. Click, please. The left side of the equation is really simple from a physical perspective. It means that a wave component, once it's running, just follows a great circle over Earth. And that is numerically very easy. It's a hyperbolic equation where the information goes along straight characteristics on a sphere. And so this stuff, most of the numerics, we actually borrowed and stole from dispersion modeling in civil engineering. Next click, please. If you get into very shallow water, then the waves change the direction. How that happens is very similar to what happens in optics. And so what happens with the lens and light going through that. And so basically that follows Snell's law. And yes, Snell's law is with one L, not with two L's, which is something that if you want to know more about, look in the footnote of my paper on my thesis in 1991. Next click, please. And then last but not least, in terms of understanding what happened with wind waves, one of the most important processes is how wind waves grow longer by energy exchange between wave components. The best way of doing that, and the lowest order way of doing that in physics, is with a 4-wave resonant interaction, which is a 6-dimensional Boltzmann integral if you do it completely accurate, which we stole from quantum mechanics. So if you look at what is in the wave model, it's already extremely multidisciplinary, just from a perspective of where we took and where we borrowed the different approaches of things we're solving, either from a physics or a numerical perspective. Click, please. And one of the things that is kind of important to know is that not all models are the same. A wave model is a forced and damped problem, not a chaotic initial value problem. And so when I talk about wave model basics, I don't even talk about data simulation, because as long as my forcings are relatively accurate, I can get a really accurate forecast without using any wave data, thanks to the fact that this is not a chaotic initial value problem. Next, please. So in terms of community approach, also that is also quote unquote sort of multidisciplinary in the sense that the wave models in the world have united in a community for a long time. Click, please. The first wave modeling was actually done for D-Day in the Second World War. The work was published in 1947 by Sverup and Monk. And Professor Monk actually lived to the ripe old age of 101 and passed away about 3 years ago. And so it's kind of interesting to be able to actually talk with people on conferences and other places that actually have started your field for practical reasons. In the 1950s, we started doing this instead of just predicting an individual wave, an individual period. We started using the spectra that I pointed out to a few slides back. But we did not do these very expensive integrals. We haven't even figured out that they were that relevant at that time. And so everybody basically tried to solve the equations, assuming some kind of spectral shape on the right side of the equation. And it was really interesting to see that all these models used exactly the same data to tune the model, and they are all equally good in idealized conditions. But then when you apply them to real conditions, they were all over the place. So in 1973, we figured out with some field experiments how important it was to have these 4 waves interact with each other. And a fun little fact here, the person who actually brought us together as a community is Klaus Hasselmann, who is one of the recipients of the Physics Nobel Prize for his climate work last year. So it's kind of cool to be able to say that our field was just a hobby of one of the folks that just got a Nobel Prize, and it's kind of interesting for me personally to know, or to be able to say that I've worked fairly closely with him for 3 decades. Then in the 1980s, the community came together and dealt with that issue of the fact that all these first and second generation models would give the same answers in idealized conditions and completely different answers in real conditions. And the community came to the conclusion that this was really because of that assumption of the spectral shape. And so we wanted to go to a situation where we solved the equations based on first principles only by having these interactions between waves explicitly calculated for. And this was important enough for Klaus and some others to be able to get the IOC to put together a SCORE work group, Scientific Committee on Ocean Research, in 1983 with a shelf life for 10 years, which was tasked to, as a global community, develop this first third generation wave model. And a seminal publication for that is in JPO in 1988. And so if you look at that from the joint North Sea Wave Project for John Swap to the future, we really have worked as a broad international community together on all this kind of wave model. And for the record, although I am not working and Noah is not working with the WAM model, and since I've wrote a separate model than the WAM model, the reason for doing that had nothing to do with the basic principles of what we wanted to do within the broader community, but with the fact that I was pretty unhappy with the software engineering of the WAM model, that didn't allow me to do research and operation with the same model at the same time. And since we could not convince the broader community to change the engineering of the WAM model at that time, we decided to build WaveWatch. Since then, the WAM model has taken over quite a bit of the software engineering decisions that we've made in NOAA. Next slide, please. And so WaveWatch by itself is also a community, and it is kind of funny how these things go in real life. I wrote the original WaveWatch for my PhD in the Netherlands. I was finished with that in 1990. Then I was hired by NASA to get that code up and running on a supercomputer, which required a rebuild of the code for the SWADE project. And then I was hired by NOAA to build WaveWatch 3 to replace and unify the models for wave modeling at NOAA. The first version was released in about 1999-2000. The second release was about 4 years later. And the first two releases were already sort of thinking about community because they were given out as freeware. And it's kind of funny how these things work. I wrote a good manual for my own sanity, and that became a sales point for the model. My family, my dad is a entrepreneur. He used to be an entrepreneur. He had his own business and own company, and I looked at how many people were doing wave modeling. I looked at the burdens that being a entrepreneur put on my father, and from these two things, I decided to just give the code away and not try to make money with selling the code. So it's kind of funny how the reasons why WaveWatch is an open and free source code have very little to do with what I'm now advertising as this being the best way of doing modeling in a community to begin with. What was really interesting is that in 2009, we put together a custom open source license. It took me 18 months to develop that with a whole bunch of lawyers from NOAA. The main reason was that when I give the code away, I had some people in some foreign countries that changed 5 lines of the code, changed the name of the model, and claimed it was theirs. And that pissed me off quite significantly. So since version 3, we have a formal copyright from NOAA on this model. And yes, that is possible, but no, I don't want to discuss that now. And there is a license with it that made this one of the first former open source licenses. And why didn't we use the Apache license or the GNU Lesser license? Well, that didn't exist yet, and therefore we had to develop our own license at that time. The big move from WaveWatch to the community was the 2008 to 2013 National Oceanic Partnership Program project. The idea of the project was to get a bunch of advances in science into operations. And yes, that sounds a lot like what we're trying to do with UFS. And we, under the cover, specifically made a very big effort there to test run how we would do code management with the community and how we could take care of that. So we used this funded project, among other things, to learn how to run a community. We picked up Subversion as a code management tool for that, which allowed us to work with 8 or 9 groups of the code at the same time, which was unheard of in that time. And if you want to learn more about the project, about the science part of it, the reference to ocean modeling is a good paper on what all the benefits were. And it really worked. In the middle of that 5-year project, we implemented a brand new physics package in WaveWatch 3 in operations, which would, if you would build a new model, would be a 5-year project. We did it in under 2 years, thanks to this knowledge we got with how to run a community. And in general, this whole community approach that we test ran out of the NOP project, a few years ago, we changed the Great Lake Waves model from a regular grid to an unstructured grid. We changed all the physics, we changed a whole bunch of outputs of it, which in the past would have been a brand new model, which have cost us 5 to 7 years, and we did it in under 18 months. So these are the hard numbers that show you that you can actually bridge the valley of death from for R2O if you do this kind of community modeling more than any other attempts that have been done to do that in the past. And we have now moved WaveWatch to GitHub. It was the first UFS model to go there as a concerted effort to get all the modeling to GitHub, although that's not essentially necessary. And the other thing that is really important is that it's not only freeware with, open source software with a license and things like that, Well, we spent quite a bit of time on building the community. So next slide. There is so there are we tracked up to the switch over to GitHub. We tracked how many copies of the code were running worldwide. We were at 2,499 copies of the code in 101 countries by July of 2018. And to give you a comparison of that, the coastal wave model from the Delft University, which is used in the engineering community all over the place, has about 3 times this kind of number. They are somewhere between 5 and 10,000 users. I don't know the exact number. But the WAM model that the European Center has less than 100 users worldwide. So the fact that this is really a community where, at least from the global modeling perspective, literally 80 to 85% of the community works with this and helps us develop this as a total global community is kind of unheard of. But that didn't happen by itself. Next slide, please. The next slide is a map of places where we held specific training sessions. So on top of this, you see Reykjavik in 2000. When the first WaveWatch code came out on the WISE modeling meeting, I gave a 1-day seminar on teaching people how to run WaveWatch. Then 10 years later, we were asked by the Indian government and by International Affairs to train up some folks in India. That became a workshop for 45 people that Arun and I ran for about a week. And when people heard about that, many more people wanted that. So since then, since 2013, we've had an annual week-long workshop for about 20-25 people at the University of Maryland. Our friends at Ifremer in Brest do the same thing once or twice a year in France. And then based on that work, we have done training all over the world. And if you look at how we did things like in Brazil and in Africa, in India and in Australia, on the previous slide, those are countries where we have a lot of users. So you can see how important it is to provide this kind of support for a community model in order to have the community there. And yes, this is extra cost and overhead for us, but it also means that as we have a lot of turnover in our Wave team right now, we have a fairly easy time in finding people who are trained in the model and who can hit the ground running when we bring them in as new people of our team. Next slide, please. So switching over to use of AI and machine learning, particularly associated with WaveWatch. Next slide. I have 3 examples here. The first example is about physics emulation. It is not necessarily the first thing people think about when they think about AI and machine learning. So we've talked about a little earlier about how important the 4-wave resonant nonlinear interactions are in the wave model. The fact that this is a 6-dimensional integral, if you do this exactly, which is roughly about a factor 1,000 too expensive to use in operational models. And so the Hasselmans, Klaus and his wife, figured out a way of making this into a 2-dimensional integral by having only one representative set of 4 interacting waves instead of every possible combination. And that created the WAM model, and that is also the starting point of WaveWatch. That was a much cheaper way of doing business, but it also introduces errors in the model. And so we've been looking for decades for better ways to do this. And one of the ways that we explored is by having a artificial intelligence emulator of the exact solutions. So next slide, please. This is something that I worked on with Vladimir for a long time. So the idea is that you have a spectrum and you have a source term, and that source term is just a mapping. It's just a mapping to go from one to the other. Click, please. And so you don't go directly from a spectrum to a source term. No, you first make that spectrum non-dimensional so that you build in scaling properties automatically. And then what we did is we decomposed the spectrum and the source term into EOFs. And the factors X and Y are the amplitudes of the EOFs for the actual spectrum and source term we're looking at. And then we use a neural network to have these amplitudes X and these amplitudes Y, or the amplitudes Y for the spectrum computed from X. And so click, please. So this works really well for individual mapping. You can get very beautiful pictures of the source terms from idealized and other spectra that way. But when you try to put it into a model, it actually does not result in stable model integrations. And the reason for that is that when the neural network creates small errors, these errors grow and they are unbounded and they are not automatically filtered out by the neural network. Click, please. So what we did, this is an invention from Vladimir, is to not only do the forward neural network from the spectrum to the source term, but also do an inverse or a backward neural network to look at the computed factors y of the source term and see if you can recompute the factors of x from the spectrum. Click, please. And then if your neural network is very accurate, then the original x and the x that you compute back by going first forward and then backward should be pretty much similar to each other, in which case you can use the neural network. If they're not similar to each other, you know that the neural network was not well trained for that specific spectrum, and then you revert back to a non-traditional physical solution. And so this actually works. Click, please. And so it creates basically a hybrid neural network web regio Tracy emulator. And it does stabilize the model. So on the left here, you see a polar representation of a spectrum of wave energy. On the right, you see, if you don't do any quality control, what the spectrum looks like with the neural network emulator. The waves don't grow. They should be 13 meters. They are only 3 meters. There's a little bit of a peak, but there's absolutely no structure to the spectrum, as you can see. Click, please. You go the wrong way. One more click. So this is allowing error to be 20% or 10%. You see that now the waves are growing, but the spectrum on the right side is not very well done yet. There's a hole in there that shouldn't be there. And by the way, these are logarithmic contours, so every contour is a factor 2 in energy. And so this is also what's making it kind of difficult to work across scale. One more click, please. This is a 5% error. Click, please. This is a 2.5% error. And you see that this hybrid method actually works pretty well. So click, please. Having said that, we would like the neural network to be better and to work in more conditions. So what you could do is you could take all the spectra for which the model didn't work, take them out and put them in a training and iteratively train to see if you can make the network more robust. That is something that we decided not to do. I'll come to that in a minute. You can also add on the right side of the spectrum some filters that allow you to get that much more smooth part of the spectrum on the right side or on the outside on the higher frequencies. That is something that we did do and that we actually use in other parts of the model to make the model more robust. Click, please. But we decided to stop this development because it was kind of obvious from the first result that there were not clear dominant scales in the interaction. So you would have to do a mapping with a large number of EOFs, and that there were too many small scales that the solution was too sensitive for. So we learned how to do robust neural networks and models. And Vladimir, if you want to know more about that, he did some work on the equation of state in the ocean and some things about microphysics in the atmosphere that actually show that you can do for these kind of problems. You can actually replace a full physics description with an emulator from a neural network. Click, please. Going to the next and kind of uncommon AI thing that I worked on. We used a genetic optimization technique. So I'll talk a lot about it a little bit later to optimize free parameters in the model. We'll stick with this nonlinear interactions. So these we worked out, both me and my Dutch friend Gerbrand, who unfortunately passed away a few years ago. We took the discrete interaction approximation, where we did a two-dimensional integral with just one representative quadruplet. We generalized that it allowed us to take a few more quadruplets, and it was applicable to both depth and shallow conditions. And then again, that would fit very well, very easy for a single spectrum, but we wanted to make sure that it worked for model integration. So we optimized that by optimizing the output of the model rather than just a single mapping. And we did that with a genetic optimization technique, and it is something that I did where Bob Grumbine taught me a heck of a lot about genetic optimization. And so we had a bunch of idealized, very cheap model runs. We had 7 mean parameters, 5 spectral parameters, and 3 two-dimensional spectral parameters that we optimized. And then we did that by describing the wave model free parameters as essentially a genome or a chromosome. We would have a population of a number of these chromosome options. We would compute for these the errors, and the inverse of the error would be a fitness or a viability. And then we would take the present generation of a set of potential solutions, have the fittest components of those create offspring by recombination and by mutation, and then see how fit your next generation was, and then go forward in generation. So that sounds a lot like biology, but if you actually look at what that means mathematically, it is effectively a directed random search. Next slide, please. And the neat thing of doing this in the genetic way is that a lot of search algorithms that do optimization of free parameters from a traditional mathematical perspective do this assuming that the functions are well behaved, are differentiable, and things like that. If you do this genetic random search, your function can be as weird as possible. It does not have to be differentiable. It can have lots of local minima, and it will be able to find a reasonably good solution and not get stuck either behind a poorly defined piece of mathematics or in a local minima. To show you how that works, I have, it's kind of hard to visualize that, but on the right, you see the 2 free parameters in the simplest possible discrete interaction approximation, which is a shape parameter on the bottom and a scale parameter on the left. I have 50 members in my population here. They are originally distributed as shown in the graphic. And for this one, I can do a fairly easy full mapping of the error space, and we know that the best solution is somewhere in the middle of this graphic. Before I'm going to show how this works. This works just as well for 20 free parameters, but I need a bigger population, and I need more generations to do that. And for 20 free parameters, I would have to do something like 10 to the 20th generation, 10 to the 20th model integration experiments to do a brute force optimization, which is of course way outside of the realistic part. We were able to optimize 20 free parameters in a highly non-linear model with about 10 to the 6th, about 1 million cheap model integration. So that is quite spectacular, and that points me to the fact that I would like to use these kind of optimization techniques for the UFS in the future too. So back to this very simple one. This is the initial randomly selected population. Click, please. This is the second generation, still very random, but it actually moves a little bit to the center. Click, please. The third generation actually really starts focusing in on the area in the middle where the error is better. And by the way, the color code is the error. So the lighter blues are where the best, the darker blues are where the best solutions are. One more click. Yeah, and click through until we have generation 10 on the screen, please. 5, 6. And if you look at this, the fit part of the population stays in the middle and gets more and more concentrated on where it needs to be. But we continuously keep sampling other parts of the solution space, and that's where the power of this technique is to go to search in error spaces with many local minima. Next slide, please. I need 3 more clicks or so. So this is actually really work. Yeah, 1 more click, please. Go ahead. So this is really work. Well, we show an example here how it really works in a real model with, which is, I did 2 things. We did a hurricane, idealized hurricane in Lake Michigan. The graphs here are for the hurricane. So the top left panel The center is where the eye is. The hurricane moves to the right. I actually have the grid moving with this, which is a nifty little feature of WaveWatch. On the right front side of the hurricane, waves are 12 meter height. On the left side, they're much lower. On the right top, you see what the relative errors in the wave heights are with the traditional DIA, in this case optimized through our genetic optimization. So the WW3, the WEM, and the G11D are traditional two free parameters DIAs, and this is the best what you get. And you see that the biggest errors occur away from where the high waves are, which means that the local spectral shape where we create the waves is not that good, and that the front runner swells are pretty inaccurate. So if you go to 3 configurations with 6 free parameters, you get the G13D, the bottom left. You can see that the errors are significantly lower if you go to 20 free parameters with 5 configurations that have more degrees of freedom in them also. You get the errors on the right side, which are only 10%. And if you look at where the 10% errors are, they are on the front left of the spectrum. So, of the hurricane. Remember that the hurricane goes from left to right here. And they are in an area, the wave heights are less than 1 meter. So we're creating 12 meter waves from the hurricane, and we get a 10 centimeter error on the left front. So this is pretty much as accurate as it gets. So the important part here is how expensive is this. So the TN in the column in the table on the left is the price of the full model integration normalized. For the WW3, the WEM, and the G11D, there is a variability in that because the solutions are not all evenly smooth, and the time step in WaveWatch depends on the smoothness of the solution. But you see that the G13D is only about 50% more expensive model and getting most of the errors out. And even with that 23 parameters, I'm only about a factor of 4 more expensive with my total model. But when I would run this model with the 6-dimensional integrals, they are in the hurricane case 1,300 times more expensive, and in the Lake Michigan case 400 times more expensive. So this is really a very interesting, different application of AI that could be used in many other models also, particularly if we do hierarchical development, and we'll talk about it more in the future. So next and last example of what we're doing in a more traditional way with the DA. Next slide, please. Oh, sorry, with AI. We normally talk about AI of getting better retrievals out of remote sensing algorithms. They're not here, or we get more information out of ensembles. And so one of our friends that has worked with us from Brazil for quite a while has worked on that quite a bit, and he's been looking at getting more ensemble information out of the wave ensemble from the wave ensemble that we run out of the gaps. And so everybody here knows how these kind of things work probably. And so from the ensemble, we typically get a better forecast of large-scale patterns from the ensemble average, although of course everybody knows here that you have to be very careful how you do that, because you don't want to have a smooth signal without any meaningful features in that. But AI can do a lot better. Click, please. And so this is an example where we were looking at wind speed, wave height, and wave period, bias, root mean square error, and correlation from the ensemble, from a traditional averaging of the ensemble, and from the neural network. And if you look at this, the gray ones are the ensemble members. The colored line that is in the ensemble members is the control run. The red is what comes out of traditional averaging of the ensemble, and the dashed green line is what comes out of a properly fitted neural network. And you can see that the neural network gets way better information out of the ensemble than anything else. And I hope that we'll be able to in the near future do a lot more neural network processing, not just of the wave model, but a lot of the ensemble data that we are getting out of the models, and get this also into things like the RTMA and URMA and all these kind of good things. So next slide, please. I want to show a little bit about private sector in the private sector collaboration here. I have to be a little careful because there are a bunch of groups that are doing this, and I just picked one group that I've worked with a lot. This is not an endorsement of that company. It is an illustration of the fact that we can work just with private industry, and the private industry is doing quite a bit of this very interesting work that hopefully can feed back into our work too. And by the way, me not endorsing this company does not mean that I enjoy working with them very well still. Next slide, please. So the company that we are working with, that I'm showing some slides from, is So Far Ocean out of San Francisco. They started their business mostly with running a much better alternative observation systems that are much cheaper than what we're using in general with very good spectral wave data, but they're also doing a lot of modeling. I'm going to run very quickly through these slides here, both because of time and both because I just want to show how broad they are, but they are a lot better in presenting these kind of things in detail than I am. So if you want to know more of them, by all means, connect with them, and the information is here and the slides will be available. So next slide. So they started with the observations. The size of that little buoy that they have is literally the size of a basketball. The funnest thing I've ever seen is Peter Smith on Ocean Ops 19 having this thing sitting on a small table and then showing me how DHS, by having him bring this as carry-on luggage on the plane, having this thing go through a scanner at the DHS and show me the picture that he took of what it looks like in a scanner on the airport. You can see how they can literally just deploy these things by throwing them overboard. That's literally what they do. They also can do it from airplanes and other things. And if you look at the bottom left, this little company has much more buoys operational in the Pacific, in the deep ocean than all the operational centers combined, and that's why it's interesting to work with them if they didn't do any modeling. Next slide, please. They also do their own forecast system, and they look at potentially using that to sell services and to help with decision support. That includes both components from the UFS and things from outside, like ECMWF forcing. And they are running a 10-day ensemble forecast with that. Next slide, please. One of the things that they are pioneering that we haven't gotten to yet is doing data assimilation, not just of wave heights, but actually inside of the spectrum. And so we are closely following what they're doing. And this is something that is potentially a really interesting thing for us to start building into our operational systems once Ocean Jedi's wave component that is just based on wave heights is in there. And next slide, please, which is the last slide. No, this is just a slide of their capability of doing spectral data assimilation to show that you get increments in your data assimilation that are not just wiped out in a local wind sea, but that actually are traveling across the big ocean bodies over long distances, which means that the impact of data assimilation would now last weeks instead of hours in terms of some of the more traditional data assimilation that we're doing, or a week and a half, I should say, not weeks. Next slide, please. And then they are using a lot of the infrastructure of the UFS to build their next generation system. So in here you can see MOM, WaveWatch 3. You can see them using NOAA land model. You see them actually using the ESMF and UOPSI, although they use a different input than we're using in our global model right now. So that is all I wanted to say. Next slide, please. Looking forward, my last slide is next, one click more. So I talked about the power of community model, the power of being multidisciplinary, and then the potential of artificial intelligence, using them as model emulators, as model optimizers, and as post-processing for results. But what I didn't talk about, and things that I see a lot around me, is using AI, machine learning, for improving DA, actually using machine learning to better understand both what we see in observations and even what comes out of the model. And there are those who think that we can use AI and machine learning to replace models or potentially just ensemble members. And for those of you interested in that, a few years back, I did a TED talk on that, on weather forecast innovations that discusses these things too. Personally, I do not think that AI and machine learning will completely replace physical modeling because our bread and butter is the extremes, and AI and machine learning tends to be more a mean state because it needs to be able to be trained properly. But then again, 50 years ago, a lot of people said that these models were just fads and that they would never replace or become really important in our forecast to begin with. So I hope that to see the next generation to be smart enough to ignore what I just said, that I don't believe that it may be replacing the models, and just prove me wrong. So thank you very much. Last slide is just a thank you. And we lost a little bit of time with technical issues, and I went a little bit of overtime, but we have a little bit of time for some questions still.
Yes, thank you so much, Hendrik. That was very interesting. If you are able to pull up the document, the questions document, that would be good. We'll see if you have any questions from anyone.
Sorry, I don't have the document handy here. Do you have? Can you just read it off for me?
Well, let's see here. Okay, we don't have any questions yet. If anyone has any questions or comments, say we have one coming through. All right. They're typing. Okay. Can you comment on a mechanism for a company like SOFAR to transfer innovations to the public sector like NOAA?
Well, this is the mechanism is really simple, because we work in the same repositories. It's more a question of whether or not your business model works with that. And intuitively, the answer is no. Practically, though, the answer is yes, that you can do that. And this basically goes back to the Linux and Red Hat business model. You have to ask yourself, where is the value as a company? Where is your value? Is the value in the software you have, or is the value in the speed with which you can create products and you can support the products and decision support out of that? And so this goes back to the Red Hat idea of giving away Red Hat completely for free and making money out of doing technical support for it. And so as long as companies like SOFAR and like Tomorrow.io and like Jupyter and others can get some of their improvement partially funded by NOAA and help them get better products, and in the meantime recognize that they will benefit and get a better business model if they also can leverage all the other progress that people have, and therefore help us get that stuff back into ours. And then thirdly, companies that see these things as selling their knowledge and their insights and their support rather than the software and the product. I think there's a broad sense of potential for these kind of models, sort for a business model where a for-profit company would still be a contributing member of a community model. Having said that, I am not that idealistic that I don't think that there are people who want to try and keep their stuff secret, and that's okay too, because the reality is that we've seen that people who try to do things on their own and keep stuff secret tend to be overtaken very quickly by the broader community that works together. So we'll see what happens. And yeah, I'm a little idealistic about this, but my experience so far is, and no pun intended there, that particularly some of the people in the younger generations are seeing that this Red Hat business model really works very well, and that they actually get benefits from sharing rather than just trouble from it. And particularly sharing your software that you're using with other people helps you a lot with maintenance of it, and with the speed of debugging and portability of your code. That is something that you yourself will benefit from too. I hope that that answers somewhat.
Okay, so the next one is, you mentioned the importance of the training sessions delivered around the world over many years. How was that funded, and will the amount of training be sustained?
So this was mostly done out of Hyde from EMC, and this is done out of Hyde from Ifremer. And in both cases, we decided that by doing that, the amount of feedback we got from other people was offsetting the in-kind contributions we did. Actually, I have to go a step back further. I developed the original training material as part of my assignment from Weather Service to UNESCO, because some of the first training sets that we did was particularly in developing countries, and we built upon that to be relatively easy to take our team and do these training sessions. I'm going to be. I've been trying to work with headquarters to actually convert the training sets from WaveWatch to Comet, or to automate them more, and to figure out whether or not we want to keep doing these in-person ones. We have a strong partnership with University of Maryland that allows us free use of all their resources, or of all their facilities for doing these kind of things. So stay tuned. We have a little bit of a gap here because of COVID, but we are looking at changing that back. In the meantime, the broader point, we've been using the NOAA funding for DTC to do similar training for the short-range weather release of the UFS, and for the medium-range weather releases. So we, as a broader community in NOAA, recognize that it is important to actually provide the resources to do the training, because that builds the community and that gives you the feedback, even in the very short term already, of having a lot more coming back from the community. And from an operational center's perspective like ours, just having a larger pool of people that we can hire that can hit the ground running when they come into our organization, particularly with our aging workforce in NOAA, is kind of important thing to do in order to guarantee continuity of operations over the next few years. So it doesn't come for free, but it's not as expensive as people think either. And this goes back to the culture change that you have to actually do these kind of things. When we started the NOB project with WaveWatch, I got a lot of pushback from the Wave team that people were saying, yeah, wait a minute, you're just going to give me a lot more work because I now have to do the code management and have to help people to integrate the code into Subversion now in GitHub. The reality was that once we've done that for a while, and once we trained our community to use Gitflow and things like that to make this work smoothly, yes, the team at EMC, the Wave team, spent a little bit more time on code management, but we spent a lot less time on transitioning codes to new hardware, on porting codes. We spent a lot of time on doing code development and debugging, and most of us ended up in doing actually much more research. So there was a sort of counterintuitive. Most people, at least in the NOAA Wave community now, really want to do this community modeling, because the extra input, or the extra time that we spend on code management is easily offset by much less time spent on traditional software building and software engineering.
Okay, and last question.
And let me add to that one thing. I'm realistic about the fact that the Wave community is relatively small. I'm realistic about the fact that the Wave community wants to work together. Some of the other communities are much bigger. So the benefit we've had with WaveWatch, we have to prove that it really works that well at scale also, and that we are able to do that same kind of thing for a much more complicated, completely coupled model in a much larger community like in the atmosphere. So last question, please. Yeah, go ahead.
Okay, so it ties into what you're saying. Will the Waves workshop be offered again in the near future?
Stay tuned. I'll have to figure that one out.
Well, thank you
I
so
hope
much.
so. I hope so. Let's put it this way. Our friends in France want to do that. I would like to do that, and we've had quite a few requests from outside of NOAA to do this. So I think we can build a coalition of the willing to do that.
Well, it'll be very beneficial. So fingers crossed, it'll be here. Thank you so much, Hendrik. Thanks for everybody bearing with us with our little technical glitches that we had today. And we'll see you again soon. Everybody have a nice weekend because it is Veterans Day tomorrow. And thank you to all the veterans. Thanks, Hendrik. Have a wonderful weekend.
Bye.
Bye.